Hello everyone. Problem of the day was transpose of matrix. You are given a square matrix of size n cross n. Your task is to find the transpose of the given matrix. The transpose of a matrix is obtained by converting all the rows to columns and all the columns to rows. Problem understanding. Today we are solving the matrix transpose problem. The transpose of a matrix is a fundamental linear algebra operation where we flip a matrix over its main diagonal. Essentially, we convert all rows into columns and all columns into rows. For a square matrix of size n cross n, this means that the element originally at position I, j moves to position j, I. The main diagonal where I is equals j remains unchanged because those elements are already in their correct transposed positions. The key challenge here is to perform this operation efficiently with optimal time and space complexity, while working within the given constraints where n can be up to 1000. Algorithm design. Our algorithm design follows a systematic approach. Since we are dealing with a square matrix, we can perform the transpose in place without requiring additional memory proportional to the input size. The core insight is that we only need to swap elements across the diagonal. We iterate through the upper triangular portion of the matrix, excluding the diagonal, and for each position I, j, where I is lesser than j, we swap it with position j, I. This approach ensures that each pair of elements is swapped exactly once. Why only the upper triangle? If we swapped all elements across the diagonal, we would end up swapping each pair twice. Once when I, j becomes j, I, and then again when j, I becomes I, j, which would return us to the original configuration. By restricting our swaps to positions where I is lesser than j, we ensure efficient single swap operation. Code implementation. Let me walk through our implementation step by step. Let me compile and run. Compilation complete. Case 1 is accepted. Key implementation details. Get matrix dimension. We first extract n, the size of our square matrix. nested loops with optimized bounds. Outer loop I runs from 0 to n minus 1, representing each row. Inner loop j starts from I plus 1 and runs to n minus 1. This I plus 1 starting point ensures we only process the upper triangle. Efficient swapping. We use JavaScript's distributing assignment to swap elements in a single line without needing a temporary variable. Return modified matrix. Since we perform the operation in place, we return the modified matrix. Complexity analysis. Let's analyze both time and space complexity. Time complexity O of n power 2. We have nested loops where the outer loop runs n times. The inner loop runs approximately n minus 1 plus n minus 2 plus until plus 1 times in total. This sums to n multiplied by n minus 1 all divided by 2 iterations, which simplifies to O of n power 2. For n equals 1000 maximum constraints. This is about 500,000 operations, which is efficient. Space complexity is O of 1. We perform the transpose in place without creating a new matrix. We only use constant extra space for loop indices and the temporary swap operation. No additional memory proportional to input size is required. This optimal space complexity is particularly important for large matrices, as creating a separate n cross n matrix would require O of n power square additional space. Edge cases and optimization. Let's consider some important aspects. Edge cases. Single element matrix n equal to 1. Our loops handle this correctly as the inner loop won't execute. J equals I plus 1 equal 1, which is greater than or equal to n equal 1. Already transposed matrix. The algorithm still works, swapping elements with themselves in the upper triangle. Symmetric matrix. A symmetric matrix equals its transpose, so swaps will maintain symmetry. Large matrices. N equals 1000. The O of n power 2 time complexity ensures completion within reasonable time limits. Optimization considerations. Cache efficiency. The current implementation has good cache locality as we access memory in a predictable pattern. Minimal operations. Each pair of elements is swapped exactly once. No division or multiplication. The algorithm uses only simple index arithmetic and assignment operations. Alternative approaches. Creating a new matrix. While simpler conceptually, this requires O of n power 2 space. Using built-in methods. JavaScript doesn't have a built-in matrix transpose function, and converting to a different format would be inefficient. This implementation represents an optimal balance between code simplicity, time efficiency, and space efficiency, making it suitable for the given problem constraints and requirements. Let me submit the code. My current stake is 377 days. All the test cases are passed, problems solved successfully. Let me push the code to the GitHub. The message of the commit is add solution for transpose of matrix problem with examples and a complexity analysis. Let me commit and push. The code is pushed to the GitHub. You can grab the code link in the description. Thank you for watching this video. Like and subscribe to News Studio for more awesome content.